I'm really glad to see you all here tonight. This is where you bring your questions and your inquiring mind. We bring you scientists, and we have a good presentation for you tonight. This is the 6th talk in our series, Building on Basics. And I don't want you to think this is the end. Please come back on April 12th, where we'll have a talk about energy transformation by Alexis Alt, a geoscientist. So mark your calendars. Let's see. I forgot to say, I'm Brynja Kohler. I'm Brynja Kohler. I'm the Associate Dean in the College of Science and also the chair of the Science Unwrapped Committee. So I get to introduce our speaker tonight and take kind of lots of credit for work that other people have done. But in fact, if you're on the Science Unwrapped Committee and you're here tonight, put your hand up high and wave. Yes, let's thank our Science Unwrapped Committee. We also have our Dean of the College of Science, Michelle Baker, here. And as we have a mathematician for you, I see lots of faculty from the Mathematics and Statistics Department. If you're a mathematician or a statistician, stand. We'd like to see you. I think, fantastic. Okay, and then very important is also our science ambassadors. If you're not sure what's going on or where the restrooms are, Olivia by the door probably gave you a die as you walked in, or Ethan. They're the ones to talk to get help. Okay, after this talk, there's, as you know, lots of cool booths where you can do hands-on activities. And tonight, in addition to the usual groups of clubs and graduate students and folks across campus and from the community, we have some new activities tonight. The Society for Industrial and Applied Mathematics, the Free Software and Linux Club is here, the ACMW, that's the Computing Machinery Group of Women, and then the grad student chapter of the American Mathematical Society and the Association for Women in Mathematics. So go check out their activities and have a cookie and all that stuff before you go home to find out the chances that USU wins the basketball game. Okay, I am very excited because following our theme of building on basics, we're delighted to hear from Dr. Erin Beckman tonight, who will speak about randomness and chance. As a mathematician, she's well qualified to address this topic. She's an assistant professor in the Department of Mathematics and Statistics. She started in 2022, so this is her 2nd year on our faculty. She teaches the Introduction to Probability course that serves not only our mathematics and statistics majors, but students from various disciplines that use probability in their fields. She also teaches a special topics course specifically about how probability is applied in mathematical biology. Erin has long had an interest in interdisciplinary work and research. She earned dual bachelor's degrees in chemistry and mathematics from the University of Texas at Austin, and went on to get her PhD in mathematics from Duke University. Then she did postdoctoral work in the beautiful city of Montreal, Quebec, Canada, at McGill University, and taught also at Concordia University. Erin spent much of her life inspired by randomness and chance of life. She says she's inspired by biology, but not constrained to it. Erin takes real-world situations, develops mathematical models by translating things into mathematical language, then solves those problems. Some of the models include population evolution, predator-prey interactions, cancer dynamics, and the spread of viruses, both computer viruses and actual epidemiological disease. Erin describes doing mathematics, and she delights in it, as a highly collaborative activity. She just beamed when she was telling me about her experience going off to the middle of nowhere in a retreat of some sort with some other mathematicians where they were provided with plenty of time for discussion, all the food that they wanted, and they could just spend the whole week developing their ideas, conjectures, experimenting, playing around with mathematical models. Then when she's not doing mathematics, she likes to listen to songs about mathematics with her family. She and her husband, Josh Cruz, who's also a mathematician, are quite busy raising their 10-month-old Amelia and their 3-year-old son, Simon. Nice to see you here tonight. Yay. The whole family loves to talk and sing about math. Erin also bikes, goes camping, and runs. In fact, she ran marathons every year for about 6 years as she was going from undergrad through grad school. So thank you. Join me in welcoming Erin Beckman to the stage.
Hi. Okay, great. Whoa, that's loud. Okay. Hi. Thanks for being here. Let me be sure that our science ambassadors are in the back and hearing me. They just walked out the room, so maybe not. Are we ready, Olivia? Okay, so we're going to do one experiment before we even start so that our science ambassadors have time to tabulate your data. So if everybody could please roll their dice once. Your dice, go ahead. It's good practice keeping it on those tiny desks, right? So now's your chance. We're going to roll dice a couple of times. Get some practice. All right, so roll your dice once. All right, now, our science ambassadors are going to count how many of you got each roll. So if you could raise your hand if you got a 1. Raise your hand big and high and hold it up. All right, good. Put them down. Raise your hand big and high if you got a 2. All right. Yes? Okay. 3. Big and high. Yeah? All right, we're halfway done. Put them down. 4. Good. Put them down. 5. All right, last but not least, 6s. A good showing for the 6s. Yeah? Okay, great, thanks. All right, so they're going to go tabulate some numbers for us. They'll come back with their conclusions. Okay, so let's get going. So as Dr. Kohler said, my name is Erin, and I'm a mathematician. And I'm a little bit biased, but I think mathematics is a great talk to have in our Building on Basics Science Unwrapped series, because mathematics forms the basis of so much of our everyday lives, and sometimes we don't even realize it. So the type of mathematics that I'm going to be talking about today, as you might have guessed, is probability. This is the type of mathematics where we're interested in describing and understanding randomness. So I do research in probability. I'm what we call a probabilist, right? But as Dr. Kohler said, I take my inspiration from many other fields like biology, chemistry, physics. The questions that I think about are inspired by predator-prey models like wolves and rabbits, how they interact with each other, how illness might spread through a group of people, or even how traits in a species might evolve over time. We can answer questions in mathematics related to these applied areas using probability. Okay, so the first thing we should clear up is, what do I mean when I say that something is random? Right? So we have our dice that we've been rolling as our example. Right? And a dice is a great example of something that's random. When I roll it, the outcome is unpredictable. Right? I roll it once, and I get a 1. Right? I roll it again, and I get a 4. Right? Now, just because it's random doesn't mean we don't know things about dice rolls. We know a lot of things about dice rolls, both from our experience and mathematically. But if you were to try and guess what my next roll was going to be, no matter how good your guessing strategy was, you would often be wrong. And this is what makes games that we play with dice so fun, because you don't know what the next roll of your dice is going to be. Dice are one of the most common examples that we use when trying to understand probability ideas, and for good reason. As a field, probability developed because of mathematicians in the 16th and 17th century who were asking questions about dice games. So it spurred an entire field with the questions that they were asking. All right, so get ready to use your dice for our experiment. Here we have a probability statement. If I roll a dice once, the probability that I roll a 4 is 1/6. So a probability is a number between 0 and 1, with 0 being it's not going to happen, and 1 being it's going to happen, almost surely. So how can we make sense of a number like 1/6? Probability that I roll a 4 is 1/6. All right, so everyone in the room, could you please roll your dice for me 6 times and keep track of the number of 4s that you roll. So roll the dice 6 times and count the number of 4s that you get. Okay, how are we doing? Are we done with our 6 rolls? Yeah? Okay, let's come back together and let's take a quick survey of the results of our experiment. Raise your hand if you didn't get any 4s at all. 0 4s. All right, take a look around, see how many people didn't get any 4s at all. All right, put your hand down. Raise your hand if you got exactly 1 4. Okay. Put them down. 2 4s. Okay. Put them down. 3 4s. Ooh, a couple of you. All right, put them down. Did anybody get 4 or more 4s? No? It's a pretty unlikely event. Oh, we got one. All right, 4 or more 4s. It's pretty unlikely that something like that is going to happen, but it can, right? Okay, put your hand down. All right, so put your hand back up if you got exactly 1 4. Okay, so look around the room. Right? This is maybe like a little bit less than half of you, right? Got exactly 1 4 in 6 dice rolls. So the probability 1/6 doesn't mean that you're going to get exactly 1 4 in 6 rolls. When we did this experiment, the majority of you didn't get that outcome. You got something different, when you rolled your 6 dice rolls. So if the probability 1/6 doesn't mean 1/6 or 1/4 in 6 rolls, what else could it mean? Well, it turns out that to see the 1/6 appearing in our experiment, there are a couple of different ways you can interpret it. But one way that you can see that 1/6 show up is to do more than 6 dice rolls. Okay, so if I'm going to need to do more than 6 dice rolls, and I mean a lot more than 6 dice rolls, I'm going to get the computer involved. Right? So I wrote a program to roll dice for us. This is doing our 6 dice roll experiment. Right? The computer generates 6 different rolls. And it rolled the sequence 2, 6, 4, 6, 1, 4. So in this case, I got 2 4s out of 6 rolls, which is like 2 out of 6, which is 0.333. Right? But now that I have it as a computer program, I can do it a lot. So instead of rolling the dice just 6 times, I'm going to roll the dice 600 times. Right? Now, I considered letting you see the 600 dice rolls flash across the scene, but it's very overwhelming. So instead of that, we're just going to see a graph of the different rolls, the proportion of them that are 1s, 2s, 3s, 4s, 5s, and 6s. So as we go and we roll more and more and more, you can see my bars changing as the proportions of 1s, 2s, 3s, 4s, 5s, and 6s changes. And in the end, after 600 rolls, I wind up with these bars showing me that the proportion of 1s is about the same as the proportion of 2s, which is about the same as the proportion of 3s, number of 3s divided by total rolls. But they're not exactly the same because this is still random. Right? If I was to do this experiment again, I would get something different. So in that version of the experiment, I got 103 4s out of 600 total rolls. So the fraction, the proportion is like
20%.
Now I did this experiment a couple more times, and you can see that every time I do it, I get a different number of 4s. Sometimes it's less than 100, sometimes it's more than 100. This time it was exactly 100. And in each of those, we need to be keeping in mind our comparison 1/6, or 100 out of 600 rolls, which is like 0.167. And you can see that these numbers are starting to get kind of close to 1/6. The farthest away is this 0.150, but that's still pretty close. And why stop at 600? It's a computer program. I'll just crank the dial up, roll the dice 6,000 times, and count the number of 4s that I see out of 6,000 rolls. Now, 1/6 would be about 1,000 of those 6,000 rolls. And I see things like 1,059 and 1,006. And if you look at the proportions, they got even closer to this 0.167. So the more and more dice rolls I do, I start to see this 1/6 appearing. And in fact, as we roll our dice more and more and more, and we look at the proportion of 4s, the total number of 4s, divided by the total number of rolls, I'll get closer and closer to 1/6. This phenomena can be explained by a theorem in probability called the law of large numbers. So the law of large numbers tells us that this proportion of 4s, which is something random, it's different every time I do the experiment, is going, as I roll more and more dice, to something which is non-random, a number, 1/6, which we know is a probability. And in fact, the law of large numbers is general enough that this applies to things besides dice rolls. And it has the same property that the proportion of things, which is random, is going, as I do more and more experiments, to a probability, which is not random. Now, I heard someone commenting earlier asking if I was a mathematician or a statistician. Right? I am a mathematician, and I'm a probabilist, and I'm often confused with a statistician. The best difference descriptor that I've heard between a probabilist and a statistician is that as a probabilist, we start with random things where we know the probabilities, and then we ask questions about them. But a statistician often starts where they don't know this side of our theorem. They don't know the probabilities. They're interested in data that's being collected from a distribution that maybe they don't know. The law of large numbers is still helpful in a situation like that, because if you were able to do random, independent experiments and find a proportion related to the thing you were interested in studying, you could make a very good guess at the probability of that thing happening, even if you didn't know it in advance. So the law of large numbers still applies to statisticians, but I am, in fact, a mathematician. So, 6,000 dice rolls that I did on my computer. Right? If you were to play a game of Yahtzee, you would have about 130 dice rolls. And if you were to play a game of Settlers of Catan, each person might do about 30 dice rolls. So finding yourself in a situation where you're keeping track of 6,000 dice rolls might not happen to the average board game player, right? But in fact, if you were to take these dice that you have in front of you and roll it 6,000 times, you would find something kind of surprising, which is that you may not see that the probability of a 4 is exactly 1/6. So let's take a look at our dice. Right? There are some things about our dice that I'm going to point out. Look at the edges and the corners. They're rounded. And if you look at the dots, which tell you which number you're looking at, those are called pips. They've been carved out by scooping out some of the material, and then they get painted with white paint. But that scooping out means that the 6, where 6 different things have been scooped out, is somehow lighter than the 1, where only one thing has been scooped out. And your rounded edges may not have been rounded symmetrically. So when you go to roll your dice, if you were to actually roll this dice in front of you 6,000 times, you may not actually see 1/6 showing up. Now, this is not a problem for those of us rolling 130 dice while playing Yahtzee, right? That's not what we would consider necessarily a large number of rolls, right? But there are places where 6,000 rolls happen regularly. If you go to a casino, for instance, they are rolling tons and tons and tons of dice all the time. And so they do see 6,000 dice rolls per day, and they have to be sure that what they're actually seeing is a dice that shows every face with probability 1/6. Now, these dice wouldn't do it, so they have something called casino die. Special die that you would use if you really wanted to be sure that every face showed up with probability 1/6. The edges are not rounded, they're sharp edges and sharp corners. And instead of leaving a hole when they scoop out the numbers, they fill it in with a white material that has the same density as the rest of the die. So you have a completely symmetric cube. And in this way, you can be more sure that what you're doing is getting a true 1/6 probability every time you roll your dice. There's actually more that goes into it than just the die. You have to roll it correctly and on the right surface. Casinos take this into account too. Right? There's a lot that goes into making sure that 1/6 actually shows up in the real dice rolling experiments. Okay, so the law of large numbers is not just for probabilities. Right? It can be applied to lots of other different things as well. So we all did our experiment at the beginning where we rolled dice, and our science ambassadors computed an average of our dice rolls. So an average of our dice rolls, suppose I rolled these 4 dice. This is what I rolled at home when I was writing the talk, a 4, a 2, a 5, and a 6. The average roll is what you get when you add all those numbers up and divide by the total number of rolls. Right? So in this case, I get 17 out of 4, which is like 4.25. Now, we did a lot of rolls at the beginning in our experiment. And my guess for what our average roll is going to be is about a 3.5. So our science ambassadors came, they gave me our number. Our average was a 3.63, so pretty close. We rolled a lot of die, and we got very, very close to a non-random number. This is, again, the law of large numbers in action. As you roll more and more die, and you take the sum of your roll, and you divide it by the total number of rolls, it goes towards 3.5, a non-random number. In fact, this number has a name in mathematics. It's called the expected value of your roll. And so we see the same pattern repeated that we saw with our probabilities. This random quantity, the average of our rolls, as we do more and more rolls, goes towards a non-random expected value. And this is the core idea behind the law of large numbers, that a random average is going to a non-random number or a non-random thing. So for our last look at the law of large numbers, we're going to step away from our dice and we're going to consider something called Brownian motion. So Robert Brown was a biologist, and in 1827, he looked at pollen particles suspended in water under a microscope. He saw something that looked like this. His pollen particles were moving around. They were jiggling in the water. Just kind of random little jiggles. And he could see this with his microscope. Now, being a scientist, he tried to explain this. He thought perhaps pollen particles are alive, and so they're moving. And so to test this out, he got some other things to suspend in water, like pollen particles from dead plants, or ground up metals and sands, inorganic things. And he saw that it didn't matter what it was that he put in the water, it jiggled randomly. Once it was small enough to be suspended in water, it would jiggle. Now, it wasn't until 1905, when Albert Einstein came along, that this motion was explained. In one of his famous 1905 papers, Albert Einstein explained that when you have a microscopic particle, like pollen, suspended in water, it's going to jiggle because it's being bumped by all the water molecules around it. Now, this was pretty revolutionary at the time because the existence of molecules was still being debated when he put this paper out there. And this was one of the big papers that supported the existence of molecules. Now, we don't have pollen in water, but we're going to do an experiment of our own to see Brownian motion. So, what I have here is a bowl with little gray beads inside of it. And these gray beads are going to represent our water molecules. And I have this big white ball, which is going to represent our pollen particle. And I'm going to turn our speaker on, and this is going to cause the water molecules to vibrate. They're going to start bouncing around. It's going to get a little loud. And I'm going to take our pollen particle, and I'm going to put it in the center. And you're going to see it's going to be bounced around by the water molecules, and it's going to travel in a random path. When it gets to the edge, I'm going to pick it up, I'm going to put it back in the center, and I'm going to let it bounce again, and it'll go somewhere different. Okay, so I won't be able to talk over the sound of the speaker, so this is what we're going to see. I'm going to reset it a couple of times, right? And we'll go from there. So we were able to see a random, erratic, jittery motion from our particle as it was bounced around by the gray water molecule beads. Okay. We can see a computer simulation of this same idea. If I have a big red particle, you can think of it as a pollen particle, or you can think of it as, we're about to do, a big dye molecule. It's being bounced around by the white water molecules as they jiggle. Right? But imagine if you were looking at this under a microscope. You wouldn't be able to see the water molecules, but you would still be able to see the dye molecule. And it would look like it was just jittering randomly. You wouldn't see the cause of the jittering, but you would still see the jittering. This motion eventually became called Brownian motion, after Robert Brown, who described it. Okay, so what can we say about Brownian motion in the context of the law of large numbers? So in that video, we could think of our red particle as just one molecule of dye bouncing around in water. But very rarely are we looking at one molecule of dye bouncing around in the water. Usually we're looking at a drop of dye in water. Now, a drop of dye has something like 10 to the 20th molecules of dye in it. Give or take a couple orders of magnitude, right? This is 10 to the 20th written out, and that's a lot of dye molecules. So we might ask ourselves if something like the law of large numbers would apply here. If I'm looking at many dye molecules, and I'm seeing their average motion, do I get something non-random, some non-random motion? Okay, for our last experiment, I'm gonna need a couple of volunteers. I need 3 volunteers to come help me with my experiment. Yeah, you, yep. 3 people, come down. Yeah. All right, so for our last experiment, what we're going to do is we're going to look at a drop of dye in liquid. So we're going to have one liquid which is hot water, one liquid which is cold water, and one liquid which is corn syrup. Okay, so let me get our camera up and running, and we'll get our volunteers to help me with this. All right. All right, come on up. So we have our 3 different substances. Can you each pour one? So one in here, this one in here, and the last one in there. Can you pour it in for us? All right, which one do you think you have over there? Hot water, cold water, or corn syrup? Let's see. You want to put your finger in it and see what it is? What have we got? Warm water. All right, so we've got our warm water here. You're going to be putting a drop of red dye in there. We've got cold water in the middle. You're going to be putting the camera is not showing. Intriguing. There we go. All right. And our last one, we're going to put a green drop. So we have our red drop in our hot water. We have our blue drop in our cold water. And we have our green drop in our corn syrup. Okay, so what do you guys think? Does it look jittery to you?
Not really. Depends on the one.
Yeah, some of them, they have some weird things going on, right? They're moving around quite a lot, but they're moving pretty slowly and pretty smoothly, especially that corn syrup one. So the temperature of the water tells us how quickly the water molecules are moving. Now we've got quite a lot of blue dye in the blue one compared to the red one, but in hot water, our molecules are moving faster. And so they're bumping into our dye faster. In our cold water, or our room temperature water, the molecules are moving a little bit slower. So they bump into the water a little bit slower. Right? Now, when you actually see this dye moving around, there are a lot of forces at play here. Right? When you drop the drop in, you get some force going, and that helps it to spread out. Depending on where in the water you drop it, there's some convection forces going on. There's some mixing happening. And that's why we have our corn syrup as our very last one. Right? A little bit of a non-standard one to drop the dye into. Corn syrup is very, very thick, so it doesn't have as many currents going on in it. And you can see that the movement in the green one looks kind of different than the other ones. What shape would you say that is?
Egg.
Like an egg. Yeah, it's a shape like an egg. It kind of started in the center and then spread outward, right? But in all of them, the motion was fairly smooth. It wasn't jittery, right? There were some weird things going on, but it wasn't jittery. It was kind of smooth and spreading. And so we do, in fact, see that when we look at the average motion of a lot of dye particles, we get some non-random motion. All right, thank you guys for helping me out with this. Let's give them a big hand. Now, this type of system, where you start with things that are microscopic and moving randomly, and you try to analyze a zoomed out version, like a drop of dye in water, which is macroscopic. You can view it without a microscope. These types of questions are being asked by probabilists today. I ask questions about these types of systems in my work. We try and make connections between small random motions and what kind of non-random macroscopic motion results from our random dynamics. So Actually doing it in the system we saw here is pretty complicated. The currents and the flows of water are very hard to describe, right? But we can do it in lots of other situations. Right? Okay, so what we saw today was applications of the law of large numbers. When we have the average of an increasingly large number of random things, we get something predictable and non-random. And it happens all over. It happens when we're looking at dice rolls and the probability of rolling a 4. It happens when we're looking at the average of dice rolls, or when we're looking at many, many molecules moving around in water. The law of large numbers is around us all the time, and maybe now that we've had an introduction to it, we'll be able to see it more often. All right, thanks, guys.
Thank you so much, Dr. Beckman. I know you're eager, so we're going to allow some folks who want to go right to those activities to leave, but after that, we'll have questions and answers. So yeah, go on out to the booths. If you want to stay for questions and answers, stay here.
Yeah, so I would recommend, so it's really good when you're learning probability. So the question was, what kind of jobs could you get as a probabilist? And what might you want to do to prepare yourself for one of those jobs? And there are lots of things you can do, things in finance, things in coding, computer science. There are jobs in everything from, understanding how to organize website traffic, how to shuffle songs on Spotify, right? All of these things involve probability and applications. So it's good to learn about probability. It's good to learn a bit of coding. It's good to have an interest in something else that can give you fun problems like physics or biology or chemistry. I've seen probability papers that study chemical reactions and how they work. So there are lots of really, really cool things, and having a good broad understanding of science, I think, is really helpful in finding the cool problems to solve that probability comes into play with. Yeah, it was a great question.
Other questions? Just raise your hand, and Ethan will bring you a mic.
Oh, okay.
I think so. We can test it.
We have a die mic for you, so.
It doesn't seem like it's on.
It could have been fun.
All right, so my understanding of computers is that they can't generate random numbers. So you create a program to generate random numbers, and I'm wondering how random it really is.
Well, so yeah, good question. So it is the computer level of random, yeah. So obviously there are a couple of problems with that, but in general, it is pretty good for something like this, right? It would be better than, say, me rolling this dice 6,000 times. So it is, while not technically random, random enough that we can get a good feel for a distribution or an experiment by using a computer to help us with simulations. Yeah, that's a good point. Other questions? Yeah.
I want to follow up on that one, but I
Okay.
had my own question, and it was when we looked at the water molecule BBs
Yeah.
and the pollen, we saw a consistent pattern of the pollen moving its way toward the outside. I wonder if you have an explanation for why it was the case that it didn't move back into the middle like we saw in the Brownian motion.
Great question. So that is a bit of real life showing up in our lovely theoretical experiment. So as a mathematician, this is one of those things we can just write off. But actually what happens is because it was on a speaker, and sound waves are waves, the force was different in the center than it was on the edges of the plate. So the beads in the center were were pushed a little bit harder than the beads on the outside, and that gave it what we would call in mathematics a drift, a motion that is dominant. So it sort of has this, and it was symmetrical. So you saw it still went in all the different directions, but because it was sort of had this peak in the center, it always went out to the side because there was more force pushing it on the beads in the center than there were on the beads in the side. It also doesn't help that there's an edge. So if you were to actually try and consider Brownian motion on the edge, you'd have to wonder, what is it doing when it hits the edge? And there are no water molecules on the outside to come back and bounce it in. And so you only get water molecules pushing it towards the edge, and then the edge just kind of stopping it. So in some way, you also had some boundary conditions going on that prevented it from popping back in. So the experiments that were done, the pollen experiments that were done, were two-dimensional, essentially, right? So you have water, but you were looking at things suspended on the top of the liquid. So essentially, you're looking at this flat surface, and it was all the videos I've seen of it were zoomed out enough that it didn't hit an edge, right? So you essentially make your space large enough so that the part you're looking at is essentially unbounded, right? Yeah. But certainly, both mathematically and in the real world, you often do have to take into consideration boundary conditions, right? And what is the particle doing? What is the molecule doing when it hits the boundary? We have different ways to deal with that mathematically, and we might choose a different one based on whatever situation we were trying to model. Yeah. I would guess so. Yeah, yeah. So when you try and model, say things like animal motion using Brownian motion, which is something that I would do, you do have to be careful about things like biases in the choice of the animals, because there's more food at the top. They choose to drift one way or the other, and we have ways to deal with that mathematically as well. Yeah, good question. All right, other questions?
This doesn't have quite direct application to what you're talking about here, but since you're a probabilist, I've never really understood the Monty Hall problem.
I just did this for my class the other day. So I wonder if I have a whiteboard marker on me. So the Monty Hall problem is a fairly famous problem. Thanks. And it goes like this. So you're on a game show, and there are 3 doors in this game show. Behind 2 of the doors, there is a goat, and behind 1 of the doors, there is a car. And we assume that you would prefer the car to the goats. And the game show goes like this. The host asks you to choose a door at random. You will get the prize that is behind that door. So let's say you choose this door. Right? Now, at this point, you have absolutely no information, and you can choose any door, and it's all the same. Right? And then instead of opening that door for you immediately, the host says, wait, I'm going to open a different door for you. And he opens a door, and behind that door is a goat. He always opens a door that has a goat behind it. Right? And then he asks you, do you want to change your guess? Right? So, what do you think? Should you change your guess or not? Who thinks change your guess? Yeah. Who thinks stay the same? Who thinks it doesn't matter at all? Everything is equally likely. Okay, so let's suppose you went into this show, right? with a strategy in mind. And we want to know the chance that you're going to win, right? So suppose you, now I'm going to have to write down some real probability to do what I'm about to do. And I'm trying to think on the spot on a way to not do it with real probability. So let me do the non-real probability, the hand-wavy version first. The host inadvertently has given you some information when he opened this door to show you a goat, right? Because he will never open the door and show you a car. He will always open the door and show you a goat. So he has given you some information, right? And that has changed the problem. It is no longer equally likely, right? Students of my class, what should we do? Should we change? Should we switch? Okay, so we should switch, right? Because the host has given us some information, right? He has opened a door that will always, for sure, have a goat behind it. And so, this door, we can show, now is slightly more likely to have the car behind it, because he wouldn't open the car door. All right, so I cannot do it for real without probability. So I'm going to try and do it with probability. Suppose you were going to switch, right? And we want to know the probability that you win the game. So you had two choices here on what could have happened, right? Maybe the door that you chose had the car behind it. The door you choose first. Or maybe it has the goat behind it, right? Now, you're coming into this with the strategy that you are definitely going to switch your door, right? The probability that your door on the very first time has a car behind it is 1/3. The probability that the door you choose on the very first time has a goat behind it is 2/3. Now, the host, when he opened the door, told us it was a goat, right? So in each of these situations, now that the door has been opened, we know what's behind the other one. If a car was behind ours, then the other door, the other unopened door, has a goat, and we lose, right? When we switch, we lose, right? Because we switch and the other door has a goat. But if our door had a goat behind it, then the other door had the car, and we switch, and we win. Now, this pathway has a probability 2/3 of winning and 1/3 of losing. So if we switch, we will win with probability 2/3. But, let's put our switch over here. If we put our stay over here, we can do the same math, right? We say our first door was either a car or a goat. Again, the probability we got the car right on the first time was 1/3, and the probability we got the goat on the first time was 2/3. But if we're going to stay, no matter what, with our first door choice, then this is the one that tells us we lose. And this is the one that tells us we win. And this one, in this scenario, the stay scenario, you win with probability 1/3, and you lose with probability 2/3. So if you go into it with the strategy of switch, you win with probability 2/3. And if you go into it with the strategy of stay, you win with probability 1/3. So it is better to switch than it is to stay. Now, it's a very reasonable question to be floored by. This question was addressed in a column by Marilyn von Savant in the newspaper when it originally came out, and it caused a huge uproar. Like, people wrote to the newspaper about how terrible she was at mathematics, and like, how could she write this, and it's clearly false, and clearly it doesn't matter what you do, and she was right. So it is a confusing kind of problem to get behind, but this is something that we can do when we've learned a little bit of probability. Yeah, good question. Other questions?
Any last questions? Oh, more.
Just about car insurance.
All right, I'm ready.
So you people know the chances of my car getting stolen tonight or me crashing on the way home. I assume that's used to set my rates.
Yeah, exactly. And it comes from, so this would be the way a statistician would use the law of large numbers. They would look at many, many, many situations, accidents. They would say, how many accidents happen in a typical day at this intersection versus how many cars go through it. This is something we could study if, say, there was a camera, a red light camera on an intersection. You could look and see how many cars go through the intersection, fine, no problem, and how many go through and get in an accident. And if they looked over many, many, many independent trials and cars going through, they could approximate the probability that you would get into an accident in that intersection. And then they could generalize it to things like cars getting stolen in Logan, right? How many people do they insure, and how many of those people get their car stolen, right? And they look at many, many people's data, and from this, they can use the law of large numbers to approximate a probability, right? And then they set the rate so that they don't lose money. It's the same as casinos. They do it so that they make money in the end based on this probability. They set it so that the amount that you're expected to pay more than covers the amount that they're expected to pay out. And because they have all this data coming in, they really do have good guesses on probability. And they can even do it, and they often do, right, for things like car insurance, they do it conditionally. An 18-year-old driver is more likely to get into an accident than a 31-year-old driver because they've had less experience. And so they actually condition it, and you can do this with probability as well, condition out on particular characteristics to get a more accurate guess as to the probabilities of particular things happening to you. The same is true of life insurance, which is why they do it often by age, and any of these other statistics where they're pooling a large number of people's data and then approximating the probability using the law of large numbers. You certainly could, yeah. So actuarial jobs is something that you could do. And yes, definitely this is one of the skills you would need to be an actuary. You would also need a statistics background as well to do something like that, because one of the questions that you have to ask that we didn't talk about at all in this would be the law of large numbers gives you a guess at the probability, but then you might ask the question, how sure are you that that's the right probability, right? We know theoretically, mathematically, that in the limit, as I go many, 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 it will converge, it will go to this number. But I'm not actually doing an infinite number of things in any of these calculations. So you need statistics to say, how sure are you that the probability that you have is right? And if you're wrong, how much will it affect your bottom line, say, in your insurance company? So you need both probability and statistics to do things like that. Yeah. Good question.
Thanks, everyone. I think there's some more activities to enjoy. If you have more questions, please come on up.
Yeah.
And let's give Erin another round of applause for this.